Of the traditional central problems of physics, there's one that we now seem to understand pretty well. That's the propagation of light through empty space. Maxwell's theory seems to tell us just about everything we need to know about that problem. Light is a wave-like disturbance in the electromagnetic field that propagates at a definite speed. Now, those are all nice words, but what do they mean? First of all, what do we mean by the electromagnetic field? Well, it's possible to detect the presence of electric and magnetic field using electric charges. If there's an electric charge in space and it feels a force, then there's an electric field present. If the charge is in motion and it feels a force due to its motion, then there's a magnetic field present. We also know what happens when the electric and magnetic fields are disturbed. A disturbance in an electric field disturbs the magnetic field, which in turn disturbs the electric field again. Energy sloshes back and forth between the two fields, and the whole disturbance propagates along at a speed which is one of the fundamental constants of nature. In principle, that disturbance can be detected in the same way that we detected the field itself, by means of an electric charge. Fortunately, we don't always have to detect disturbances in that way, because we come equipped with built-in detectors of disturbances in the electromagnetic field. They're called eyes.
The eye is one of nature's most versatile instruments.
One more time.
And from the first visionary onward, the human race has tried to broaden visual experience well beyond its collective nose, to extend eyesight into the wonders of the world, large and small, near and distant.
Clear? Pretty clear. What about with this side?
Of course, for a thorough examination, that takes not only a perception of light, it takes a clear perspective on its properties. And the properties of light are best seen in the simple fact that light is a wave. That means light must have properties that are common to all waves. For example, waves can spread uniformly outward from a single point disturbance. But waves from a carefully coordinated array of point sources can add up to form flat wave fronts called plane waves. Plane waves, in turn, can be made to spread out again, because waves bend around corners. And when wave fronts encounter one another, they can interfere to produce stronger waves or weaker ones. Certainly, water waves do all these things, but can it be that light waves do them too? Seeing the connection between water and light may be much harder than seeing the handwriting on the wall. For example, no one tried harder to extend the conventional view than Galileo. But as he saw for himself, not everyone sees things in the same light, nor accepts that which is new at first glance. But by 1610, at least to a certain extent, he had a very powerful tool with which to make his argument. Although contrary to popular opinion, Galileo didn't invent the first practical telescope. He made the most extensive use of it. And at the turn of the 16th century, his simple refracting telescope zoomed astronomy toward the future. As his sketches reveal, Galileo saw Saturn's rings and sunspots, the phases of Venus, the moons of Jupiter, and the craters of the moon. If a man can finally see the large and distant, Galileo must have wondered, why not the very tiny and close at hand? And with a question of that nature, he peered through another invention for which he's given credit. It was the compound microscope, and as his sketch illustrates, with its crude but magnificent power, Galileo was able to see an ordinary Italian bee in extraordinary detail. As he'd done in the science of astronomy, here he had also made an enormous advance in the field of optics. Contrary to another popular opinion, eyeglasses aren't as new as they often look. In fact, in an array of models since the 13th century, they have continued to create quite a spectacle. However, while the frames have been subject to this or that designer's whim, the lenses have usually been based on an unchanging scientific principle. This principle applies to the lenses of microscopes and telescopes as well, and it's called refraction. Refraction occurs when light enters a medium, such as glass, and bends. To make use of this phenomenon, makers of glasses, microscopes, and telescopes can grind curved lenses that focus light to a point. But before that, it's possible to see refraction in its natural state. And here's a clear-cut example. A glass prism not only bends or refracts a beam of light, it also reveals that plain white light is composed of all colors of the rainbow. This process is called dispersion. And it was seen very clearly by Isaac Newton, who investigated both refraction and dispersion. According to Newton, light was made up of particles that, obeying the law of inertia, traveled through empty space in straight lines. For Newton, refraction, or the bending of light by matter, could be explained by the gravitational attraction between light and matter. However, at about the same time and on the same subject, an opposing viewpoint arose in Holland. Christian Huygens, a Dutch physicist and astronomer, theorized that rather than being composed of particles, or corpuscles as Newton called them, light was made up of waves, and in the long run, his idea would be seen as the correct one. A wave is a disturbance that propagates from one place to another. And no matter whether they're electromagnetic waves, or water waves, or any other kind of waves, all waves have certain properties in common. For example, a wave's frequency times its wavelength equals its speed. But mechanical waves can be longitudinal or transverse. While electromagnetic waves are always transverse, and in empty space, they always travel at the speed of light. But although they always have the same speed, they can have vastly different frequencies and wavelengths. And in doing so, these waves go so far as to create the entire electromagnetic spectrum. As a matter of fact, only when electromagnetic waves have a wavelength in the narrow range from 4 to 700 nanometers are the waves visible light. That is the spectrum from red to violet. Even shorter wavelengths, called ultraviolet light, are radiated by the sun. Though these invisible rays are dangerous to living things, they're absorbed and rendered harmless by the ozone in the Earth's atmosphere. Shorter still are X-rays, with wavelengths the size of atoms. And finally, gamma rays, with the shortest wavelengths of all. Gamma rays, with wavelengths as tiny as the atomic nucleus itself, are created by nuclear reactions. Longer wavelengths, extending to visible light and beyond, can be created or absorbed when atoms change from one energy state to another. Beyond visible light, there's infrared. With wavelength longer than red light, infrared radiation can be detected only by the heat it deposits. The universe is suffused with long wavelength radiation, seen as the cooled remnants of the Big Bang that started it all. That includes not only infrared radiation, but also microwaves. Microwaves are the first part of the spectrum whose frequency is low enough to be generated by human-made, alternating current electronic circuits. The universe is likewise full of radio waves. Centimeters, meters, or even kilometers in length, radio waves complete the electromagnetic spectrum. Of course, the great Michael Faraday didn't live to see the electromagnetic spectrum. Nevertheless, it began to take shape when, envisioning electric charges surrounded by lines of force, Michael Faraday asked himself a question. What happens when these lines are set into vibration? Faraday didn't quite see the whole answer, but he wouldn't have been surprised by the picture that emerged. An oscillating electric charge creates waves that propagate along the lines of force at the speed of light. These ripples are transverse waves in the electric field, propagating in wave fronts that become flatter and flatter farther from the source, coming more and more to resemble the plane parallel wave fronts that are called plane waves. As the wave fronts pass through each point in space, the electric field vector oscillates up and down, marking the passage of peaks and valleys of the propagating wave. Thus, an oscillating electric charge is indeed the source of outward spreading ripples in the electromagnetic field. It took James Clerk Maxwell's theory to explain the nature of light and to project the image of the electromagnetic spectrum as a whole. But for all his amazing insights, Maxwell wasn't the first to see light as a wave. In the early 1670s, Christian Huygens formulated a principle of light waves, stating that every point on a wavefront is a source of new waves. And in 1801, despite the prominence of Newton's rival-corpuscular theory, another Englishman, Thomas Young, proved beyond a shadow of a doubt that light is a wave. He accomplished that by proving that light has the wave property called interference. Wave interference can be seen to be constructive or destructive. If the waves, as they travel, encounter each other in step, they can reinforce each other, create a stronger wave, and produce what's known as constructive interference. But when they're out of step, waves can cancel each other completely. In other words, destructive interference. As Thomas Young suspected, all waves in all media behave in this fashion. And to prove that light is a wave, he merely had to illustrate that light exhibits interference, the behavior common to all waves. Here's the principle. Light from a single source enters two slits, which are side by side and not much farther apart than the wavelength of the light itself. After passing through the slits, the light shows up as a distinctive pattern on the screen. When a single plane wave encounters two slits, each slit becomes the source of spreading wave fronts. And because both new waves originate from the same plane wave, their oscillations are synchronized. The result is a stable pattern of up and down ripples, alternating with directions along which the waves cancel one another. This produces a pattern of bright fringes of constructive interference on the screen, separated by dark fringes of destructive interference. And that was it, a series of alternating fringes to prove that light is a wave. It was a conclusive demonstration, and ever since, physicists have had to explain the behavior of light in terms of the properties of waves. For example, if light waves, like all other waves, bend around corners, how can it be that light can cast a well-defined shadow? The answer can be found in the relative magnitudes of the wavelength of the light and the size of the opening through which it passes. The shorter the wavelength, the less completely the wave spreads in all directions. Even with a wavelength equal to the width of the opening, the beginnings of a shadow can be seen. The shadow is really due to destructive interference of light from different parts of the gap. And the result of it all is, the shorter the wavelength, the more nearly the light emerges in a well-defined beam. The wavelength of visible light, hundreds of nanometers, is so small compared to the sizes of normal objects that they can cast very sharp shadows indeed. But that explanation doesn't shed much light on an even more important question. Since everything ever seen is the result of light encountering matter, the question is, what is the nature of that encounter? And the answer is, since all matter is electrical in nature, it all comes down to light waves and electric charges. For example, when a light wave encounters an electric charge, the oscillating electric field makes the charge oscillate, which creates a new outgoing wave. Notice the shadow that forms behind the oscillating charge. A line of electric charges, they might be electrons bound to atoms in a crystal, can produce outgoing plane wave fronts in new directions. And if the charges are free to move easily, as are electrons inside a metal, the result can be to stop the wave from penetrating at all. Instead, the wave is completely reflected. This is mirror reflection, in which the angle of incidence is equal to the angle of reflection. That's true no matter from what direction the beam arrives. But reflection can also be described in a different way. Of all the possible paths from source to mirror to destination, the true path is the one that arrives in the shortest time. Because a metal surface with its mobile electric charges is just what it takes to bounce the light back, mirrors are made of silver, which is plated onto the surface of glass. But if that's why mirrors work, why do lenses work? They work because when light travels through a transparent medium such as glass, the continual reconstruction of the light beam by each molecule of the material makes for slow going. In other words, the speed of light inside the glass is slower than it is out in the air. When a light beam, incident at an angle, first encounters a piece of glass, one side is slowed down before the other, forcing the wavefront to change direction. This bending of light, whether in glass, water, or any other transparent material, is called refraction. Light is refracted closer to the direction perpendicular to the interface whenever it enters a medium that slows it down. This occurs no matter what the direction of incidence. And as in the case of reflection, of all the paths that light could follow from source to destination, the one that arrives in the shortest time is the true path. Whether in reflection or in refraction, the principle of shortest time chooses the unique direction along which wavefronts are reconstructed by means of constructive interference. Eyes have a built-in lens, and it tends to refract entering light, and thereby form an accurate image on the retina.
Does that look pretty clear?
If the eye's lenses aren't refracting properly, artificial lenses can come to the rescue and bend light to focus images on nature's behalf. Of course, refraction often entails another kind of distortion, because the refraction of light depends on its color. Light of different colors, initially mixed together in white light, is spread out into a rainbow of colors by this prism. This is the phenomenon of dispersion. It's the reason why, despite all its noteworthy power at the time, Galileo's telescope, a refracting telescope, was actually rather limited. But Isaac Newton realized that a prism and a lens affect light the same way, which meant that the refracting telescope would remain limited. And that's the reason why he invented the reflecting telescope. As it encounters a reflecting telescope, a beam of light reflected from a parabolic surface is reflected to a single point at the focus of the parabola, without dispersion, regardless of color. And that's why, ever since Isaac Newton invented it, the reflector telescope has been the handiest tool of the optical astronomer. Of course, light isn't the only wave in the heavens, nor the only kind of wave that encounters a mirror and bounces back. Just as light waves reflect, so do radio waves. That's why the principle behind radar and the telescope are one and the same. The dish of a radar reflector has the same parabolic shape as the mirror in a telescope. So, whether it's the Coast Guard's indispensable radar or the latest design of a 10-meter optical telescope, the object is to detect electromagnetic radiation, following on the same laws and reflecting off similar metal surfaces. No matter the object, from an eye chart at a few meters to an incredibly distant star in the reflecting lens of a modern telescope, light waves continue to reveal the most amazing sights. And to a certain extent, the journey's just begun.
Once we understand that light is a wave, many of its peculiar properties become comprehensible because they're just properties of waves. But in the case of light, what is it that brings light from the sun through empty space to the Earth? What's waving? There being no obvious answer to that question, 19th century physicists at least gave it a name. It was called the luminiferous ether, And it was what waved when light passed through. It was the medium that transmits light in exactly the same sense that the air is the medium that transmits sound. Throughout the 19th century, a number of ingenious experiments were done in an attempt to detect the motion of the Earth with respect to the luminiferous ether. For one reason or another, all of those experiments failed. And then in the 1880s, Albert Michelson designed an experiment of exquisite sensitivity which used the interference of light waves themselves as a measuring tool to detect the motion of the Earth through the ether. The story of that experiment and its repercussions and consequences is what we'll speak about when we meet again next time.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.